Welcome to lecture 23 on Fermat's last theorem. So this will be a relatively short lecture, and I probably won't teach you a single calculation in this lecture. But I think it's an important story to acquaint you with because it's kind of one of the, if not the major story that happened in number theory in the past century, I would suppose, but perhaps several centuries, you could argue. And so the story goes like this. Back in the 1600s, about 1620 or so, a fellow by the name of Bechet or Bechet, I'm sure I'm mispronouncing it either way. Anyway, he translated to Latin this ancient work on arithmetic by Diophantus. All right, and so the way it worked back then is they have these great works in the library or something, and if you had access to this library, perhaps of a noble or somebody, then you maybe go read the book, and if you're like Fermat, then you write some notes in the margins. All right, that's a practice which is, I think, generally discouraged in today's libraries. Like, I've never been encouraged to write in the margins of books at libraries today, but it is kind of a fun idea, right? Like, just write little notes in the books you read for other people to read. It's kind of fun. But this is what Fermat wrote in the margin of this, great book by Diophantus. He said, there are no positive integer solutions of x to the n plus y to the n equals z to the n for n greater than or equal to 3. Now this is kind of surprising a little bit because, we've seen tons of solutions for n equals to 2, right? X squared plus y squared equals to z squared. Well, that's the Pythagorean triple problem, and we saw that we can generate all kinds of solutions to that, right? So why does it stop working at 3, and yet it does, all right? Or so it seemed to be a claim that it didn't work for 3. Now, Fermat claimed to have a proof, but he said it couldn't fit in the margin. And it remained without proof for general n for about 350 years. A proof technique known as the method of descent solved Fermat's last theorem for particular choices of n, but each such proof involved idiosyncrasies of the choice. So here's a couple of notable ones. Euler in 1753 proved it for n equals to 3. Dirichlet and Legendre in 1825 proved Fermat's last theorem for n equals to 5. Lamé in 1839 proved it for n equals to 7. All right. So all of these were proofs that in one way or another were based on this method of descent, which was introduced by Fermat, which I have not included in your course. Sorry. But anyway, so the hope for a general argument was kind of low until 1984. Something kind of surprising happened. Frey, Ribet, and Sayre, I'm sure it's probably Ribet, but anyway, these three mathematicians who are spelled correctly but mispronounced in this lecture right here, they show that there was a connection between elliptic curves and Fermat's last theorem. All right. So elliptic curves also come up in the discussion about the next step of encryption. All right, past the RSA encryption, elliptic curve encryption is like the next thing that seems to be people are thinking about. So that's a kind of a next. If you were to take another course in number theory, an advanced one, maybe you get to look at these elliptic curves in class field theory and some of the beyond this stuff. Anyway, so these guys showed there was a connection between elliptic curves and Fermat's last theorem. In particular, in the 1950s, Taniyama and Shimura, they made a conjecture, and that conjecture was shown to imply the FLT. So these guys are the ones that showed that the Taniyama and Shimura conjecture implied the FLT. All right. Then Andrew Wiles, in June 23rd of 1993, he outlined a proof of enough of the Taniyama and Shimura conjecture to imply the proof of the Fermat's last theorem. And it took until, so there was a couple, apparently, if you know what you're doing, obvious gaps in his proof. So within the day that he announced it, there were people like, hey, flag on the play. What about that? And but the idea was right. it took another, year and a half, 2 years of careful work and joint work with a fellow named Richard Taylor. The full proof was about 200 pages, but it did work. They did prove enough of the Taniyama-Shimura conjecture to imply the Fermat's last theorem. And you can read pages 217 to 237 of Jones and Jones Elementary Number Theory for more details on this story here. But what's perhaps, so I should mention, there was a fellow I worked with when I worked a year for the Navy, so to speak, and he was a math major, undergraduate, and he actually had a proof of Fermat's last theorem that was really, really close to being correct, but not involving any of this kind of sophistication. Really just sort of like arguments along the lines of, say, binomial theorem kind of arguments. And there was like one sign error in his argument that kept it from being right. And I tend to think that, like, maybe what that friend of mine found there, like that very plausibly could be the proof that maybe Fermat thought was a proof but actually wasn't. I don't know. You can conjecture what exactly it was that Fermat was thinking. Who knows, right? But what's interesting though is, so like if you found a more simple proof of Fermat's last theorem, people would be like, good job, right? But I mean, you probably would get a professorship from it or something, I mean, who knows? But actually, this proof that involved this really bizarre thinking about elliptic curves and everything, it wasn't just a throwaway, one-off kind of thing just for Fermat's last theorem. Actually, the technical tools which Andrew Wiles used in that proof opened a whole new door of investigation and discovery in number theory. And so it has revolutionized, as I understand it, and I'm no expert, number theory since that time. So these new techniques involving modular forms, besides proving the FLT, the techniques brought a renewed interest in number theory. And in fact, modern number theorists use many branches of math to unravel hard questions. Like, to be a modern number theorist, you don't just know number theory, you need to know a little bit about a lot of different kinds of math. Analysis, algebraic geometry, topology, abstract algebra, representation theory, a lot of things, Lie theory. So that's part of the attraction of modern number theory to pure math majors. It's sort of one of the more interesting places to work these days. It never appealed to me much because I was always interested more in physics, but actually, number theory, my first place I was forced to care about number theory was I was interested in going to grad school for string theory, and I asked the professor I was visiting with, I was like, but you don't need all math, right? You don't need number theory. And he's like, oh no, I use number theory. I was like, because I'd been focused on other kinds of math. I was like, God, man. So it's everywhere. Anyway, let me just say a little bit more. Let me say a little bit more about, setting aside the groundbreaking, highfalutin modular form mathematics. What did the people of the 19th century try and fail to do? Like, what were they successful in? So I have taught number theory before out of Stilwell's number theory book, and when I taught it out of that, the first time I taught it, I actually presented this proof, if I remember right, that you can look at what are called Eisenstein integers. So the Eisenstein integers, you adjoin the third root of unity. It actually has a Euclidean domain, and you can factor x cubed plus y cubed like this. And since it is a unique factorization domain, then you can leverage the equation above to supply a contradiction if a positive solution exists. And again, I think it has to tie in. I'm not sure if it actually tied into the method of descent by Fermat or not. It's been a while since I proved it, but anyway, you can prove this. It's not impossible. It takes about, 2 lectures, maybe about 2 hours a lecture to carefully present the proof of this. It's on page 132 to 134 of Stilwell's Elements of Number Theory. But, this is just a specific case, right? Fermat's last theorem is for any n greater than 3. So this is just like, a very small part. Okay? And just to let you know, this is kind of interesting. So why can't you just use z adjoin the square root of minus 3? Well, square root of minus 3 is not a unique factorization domain. So like the number 4, you can factor it into 2 times 2, or you could factor it into 1 plus root minus 3 times 1 minus root times minus 3. And 2 and 1 plus or minus root minus 3, these are not associates. Like, it's not multiplication by a unit that gets you from here to here. These are inequivalent factorizations in z adjoin the square root of minus 3. On the other hand, once you adjoin the third root of unity, then these two different factorizations are just different ways of writing the same factorization, because you get these, the third roots of unity are units, so you can multiply by like zeta 3 times zeta squared, and when you do that, that's just multiplying by 1, and so you can convert 2 times 2 to this times that in the Eisenstein integers. So you might be tempted to think that, oh, okay, so I can always just, enlarge my number system enough to make this kind of thing work. Like, there's got to be a unique factorization domain that I can get to just using sort of complex multiplication, but I actually not so. So in particular, Lamé, 1847, used cyclotomic integers. So that means circle cutting. So you know how the roots of unity cut the circle into p parts? It's like that, right? So z adjoined the pth root of unity for an odd prime, and he thought he got a proof of the Fermat's last theorem from that, based on that, the Fermat's descent argument paired with this mathematics, that x to the p plus y to the b can be factored into the product of x plus y, x plus I zeta p, x plus y zeta p squared, and so forth and so on. It is true that this factors into that, but what's not true is that these give you a unique set of prime factors. So like it's not a UFD, right? It's not a unique factorization domain. So when you try to compare this to the other thing to get the contradiction you want, it falls apart. So in other words, since z adjoined zeta p is not a UFD, the argument by Lamé fails. And this led, amongst other things, Kummer to introduce the concept of ideals, in part to repair this fault. Anyway, you can read Stilwell's Elements of Number Theory for more about this story, or you can study class field theory, which is beyond that book, I suppose. But anyway, I just wanted to give you a sense of, these things that I'm talking about here, they kind of roughly tie into some of the things we've discussed in this course, right? Like the Gaussian integers. The main theme here is to use an extended number theorem, number system, to sort of crack open a formula that you're looking for, integer solutions. So you're looking for integer solutions, you go beyond the integers to make the problem simpler, and in that extended domain you're able to solve it. Just like we saw the cubic equation, we extend to the complex numbers, right? And then we can find a solution. And this theme we see over and over in mathematics, right? You take the problem you're given, which is concrete, and you abstract to something that's, more general, and that maybe gives you the intellectual wiggle room to solve the problem. But anyway, there of course is more to talk about in number theory, but with this your course has come to an end. My apologies for all the mistakes and the lack of secret words. I guess I'll give you a secret word. The secret word for this one is nickel. There we go. Thanks, guys.